when Benoit asked for a title, I said, well, organometallic approach to complex nano-object is a very nice title because you can put anything you want. And complex, of course, is much more fashionable than to say an organic approach to simple nano-object. But I will mostly speak about simple nano-object. So what do we mean by organometallic approach? You know, when you are making nanoparticles, very often you use high temperature, and the high temperature can be used, as we have seen before, to make perfect nano-objects, to crystallize them, but also it is useful for decomposing the precursor. And the idea is if you bring the energy to, no problem. If you bring the energy to transform your precursor to another precursor, which is a high energy, then you will need just a little bit of energy to decompose the precursor. I said in my introduction, thank you very much, Benoit, for the invitation. No, you know, otherwise he will not invite me anymore. So if you have a high energy precursor with a little bit of energy, you will decompose. And since you have not a huge barrier to cross, then maybe you can have some small intermediates and some, you can see some things that you would not be able to see by heating a lot. So that was the initial idea. And so organometallic approach, the main thing is the choice of the precursor. The chemistry is very rich, and so we can have precursor which will decompose, not as we want, but almost now. Characterization of the surface, another advantage of organometallic chemistry is that you can design precursor which will not leave anything at the surface when they will decompose. And I will show an example. And so you have a clean surface. But of course, the surface has always something. Even in ultra-high vacuum, you can find things attached to the surface. So there is no naked surface. And then study the surface chemistry and also use molecular characterization techniques like NMR. So how it started, Benoit put the pressure on me saying you will see many important people, so behave yourself and prepare some historical, yes, he told me, and prepare some historical talk, so I will try. Huh? So it started actually in 1981 and had nothing to do with nanoparticle and with quantum dots. This is this paper of John Spencer and Gordon Stone, and they use platinum zero precursor to make hydride clusters of platinum. And I wanted at that time to make hydride cluster of ruthenium. Everybody was making carbonyl cluster of ruthenium. And they had no chemistry because the carbonyl will remove the electron from the surface of the ruthenium. So I took a precursor zero valent prepared by Vituli and Perticci in Italy, ruthenium cyclooctadiene, cyclooctatriene, and this precursor, you just feed it a little bit with hydrogen at room temperature or below, and it decomposes. So nice. And some ligands, and we got this compound, ruthenium dihydride bis dihydrogen. And that kept us busy for 25 years. And still some people are using it because it's an extremely reactive molecular complex. Well, a few years later, John Bradley, a good friend of mine who had been postdoc with Wilkinson when I was doing my thesis, came to the lab and he was trying to decompose ruthenium carbonyl. And I told him, I have a better choice. And that was 89, and we started to decompose ruthenium cut and make nanoparticles. It took us 2 or 3 years to get an electron microscopy because the physicists said, we will never introduce chemicals in our electron microscope. And finally they did, and it started like that. So at the beginning, we used polyvinyl pyrrolidone or other cellulose acetate, cellulose nitrate to stabilize the particle, and we got monodispersed, more or less, small particles, and this is our first high-resolution electron microscopy from the early 90s, which was not too bad, actually. I don't think you can see it, but... And we use a lot wide-angle X-ray scattering because we are below the diffraction limit, and so we could not have XRD. And putting CO13, we tried to measure the CO adsorbed on the nanoparticle in solution in order to see if the surface is accessible and where would CO bind. And actually, we managed, this is an experiment which was done in solution in Exxon, in Annandale, and it ran, I think, for 4 or 5 days to accumulate. And now we do that by standard MAS, solid-state NMR. Then the next step was magnetic nanoparticles. Somebody asked me, can you do it? There was this precursor. It took us a while to make it, cobalt cyclooctenol cyclooctadiene. Actually, it took us, but when we got it, then it's very easy to get nice nanoparticle. And the good thing about this nanoparticle, you can see the TEM from that time, is that we could make 2 sizes, and this size were measured at very high field, up to 30 Tesla, and they have an increase in magnetization compared to the bulk. And that had only been seen in ultra-high vacuum. So the nanoparticles prepared by organometallic chemistry can compete for the physical property to nanoparticle prepared in UHV. It has been very hard to publish that. And the physicists would not believe it, but finally it was published, and this is my most cited paper. So we can stabilize the particle by polymer. This is a steric stabilization, but we can do simple organometallic chemistry, put ligands. And the ligands will coordinate exactly in the same way as they coordinate on a molecular complex. And for example, if you have this N-heterocyclic carbene or a phosphine, like this diphosphine, the chemical shift that you can measure on a small particle is very similar to what you can measure on a simple molecular complex. So this is organometallic chemistry. This is not a surfactant. And here, this is a model on how the very nice model made by the theoretician on how the carbenes coordinate at the surface. Well, we make the particle under hydrogen, and the next question, and of course, ruthenium nanoparticles are very good hydrogenation catalysts. So the next question was, do we have hydride? And the following question was, how do you measure the hydrides? So we tried to measure that by HD exchange. We feed the particle isolated with D2, and we measure HD. We can discriminate. Sorry. And the next and more easy thing is isolate the particle, feed them with an olefin, and measure the alkane which is produced. That shows that we have about 1 to 2 hydride per surface. It will go to the non-polar you know, there is an organization of the ionic liquid, and it will go into the non-polar domains. Okay. So the next question was, can you see the hydrides, and where are they? Are they terminal, bridging? And for that, we used deuterium static NMR, an old technique also used in biology. And I will not enter into detail, but with the help of the theoretician, we could model what we would expect and simulate the spectra. And in one case, where we prepared the ruthenium nanoparticle into a cage, molecular organic framework, there is no ligand at the surface, then we could see that the hydride are dynamic down to 20 Kelvin. So at 40 Kelvin, they start to move at the surface of the particle, which means that the barrier to move at the surface is extremely low. So there is a high dynamic on the surface of this particle. So what do they do? This is out, I will not go into detail, but for example, the latest results that I show first is that we can selectively label a molecule of biological interest. This is nicotine. This is of some interest for some people, but not to all. But nicotine can be selectively deuterated in the alpha position to nitrogen. And also, we can label enantioselectively amino acids like that. So we play on that. And of course, it does catalysis. Okay, so this is the preparation of metal nanoparticle. And I would say on the first step, decomposition, we freeze, what do we have? Then, is it general? Well, we tried with oxide, and we took a high-energy precursor, zinc dialkyl. Some of you may know that in a glove box, if you want to see if you have a trace of water, you take zinc dimethyl. And when it fumes, it means that, and when you take it outside of the glove box, it makes blue flames. Very nice. You can try. Huh? But, so this is a high-energy precursor. The cyclohexyl is a little bit less reactive, but still. And then we feed it in solution with water from the gas phase, either water brought by an argon stream, or even we can open the flask. And then we can make like that zinc oxide, which is crystalline. And playing on the ligand, on the rate, we can have zinc oxide of various size and shapes, rod-like, spherical, long rods, etc. The interesting thing is that zinc oxide at small size is it's an ideal system to study the coordination of surfactant at the surface. So we could play with acids, amines, here is octylamine or hexadecylamine, and we could play with different NMR techniques. Again, I will not enter into detail, but the DOSI here allows you to measure the diffusion of the particle into the solution. And then, if the ligand is strongly attached, it will diffuse with the particle. If it is not, it will exchange. And then you can measure the rate of exchange at the surface, and you can see what your ligand does at the surface. And the other thing is that between two ligands, similar, we can see if they see each other. And the funny thing, what we found, is that they see each other, but not the way you would anticipate, because one is linked to ZNO, and the other one goes to the other direction. So there is a very complicated chemistry at the surface with interdigitated amine ligands. And we have seen that by the EXI techniques. Okay, so we played with oxide, and we do, for example, gas sensors, and the rods are quite good to gas sensing. And we work with companies on that. Now, quantum dots. Well, we have heard many interesting talks about quantum dots, and we have seen that the methods to prepare the quantum dots are working very well. So nothing to do here, or not much. There is one point where maybe there is room for improvement, is indium phosphide. Of course, we have the expert in the room, Peter. But maybe we can see what happens there. Why don't we grow larger particles? So we started from this preparation, which is a very good preparation to give small nanoparticles published in Nanoletter by Peng. And let's look. Why doesn't it grow? The answer is here. It's solid-state phosphorus NMR. When you look at the solid-state phosphorus NMR, we have two information. First, this is the NMR of the phosphide in the core of the particle. Nice, there is a lot. But there is another peak here. This is a phosphate. A phosphate means that there is oxidation. To be sure that the phosphate is at the surface of the particle, what you can do is a cross-polarization experiment. You transfer the polarization of a proton, which has a high polarization, to the phosphorus. The protons are at the surface of the particle. So what you expect is that the outside peaks will increase their intensity, and the inner peak will decrease their intensity. And what we see is that the phosphate increases in intensity. So where do they come from? To find an answer to that, we put a little bit more water, and you see what happens. When you put water, you oxidize. Next question, where does water come from? And then to make a very long story short, it was found that in those conditions, you have a reaction of somebody, I don't remember the name, but where you couple the two acids to produce a ketone, and then water and CO2, and the ketone was fully characterized. So even by this organometallic technique, glove box, etc., we produce water and we produce oxidation. So, and then what we find, and I will be quick on that, is that the carboxylic acid is very strongly attached to water, to phosphate, covers the surface, and then nothing can happen. It's a rock, finished. Okay. Next question. We will take a more organometallic precursor at lower temperature. So probably it will work. It does 1.5 nanometer. It's not very luminescent, and we produce water, a lot of oxidation, and this time we produce water by the formation of amide. So next, we put hydrogen. Hydrogen will remove the water from the surface of the growing indium phosphide. We have, I did not put the size of the particles, they are 3.9 nanometer. And what we see is we have less oxidation, but still oxidation. So as soon as we have amine and acids, and we heat, there is a lot of organic chemistry which is known on that. And a lot has been done in the 19th century here and around. So not very hopeful. So fortunately, sometimes when you don't hope, there are good things which happen. So we tried with the preparation of cadmium phosphide, essentially because in principle with cadmium phosphide you can have some emission in the infrared, in the biological window. And of course, cadmium phosphide is a good alternative and much safer than cadmium selenide because there is no selenium, but it's cadmium which is more toxic. But anyway. And what was published is also high temperature synthesis. But what was found by people who are actually in the room, Will Solojo, Céline Néral, and Fabien Delpech, is that if you solubilize your cadmium acetate before the reaction, you have a soluble complex containing acid and amine, and that you can feed with your sulfur precursor at room temperature, and you get crystalline cadmium phosphide. Then, here it's a high resolution, everything is okay. And if you look at the NMR, you see that, in fact, on top of cadmium phosphide, there are some acetates, which are coordinated, and a weakly coordinated amine. This is this, the exchange. We can discuss if somebody is interested in DOSI afterwards. And no oxidation. You know, if you remember well, there was a peak in this region. But if you work at room temperature, there is no degradation of the ligand, and so no water formation and no phosphate formation. Since there is no phosphate formation, you can adjust the size that you see by adjusting the luminescence. And you can work even at 90 degrees to heat a little bit, and you can adjust the size of the particle. The good thing also is that you can grow, well, not a zinc sulfide layer, but put zinc sulfide at the surface, and it becomes air stable. So we can have air stable cadmium phosphide. Now the question is, can we go further? Can we come back to indium phosphide with this result? And it's not clear, unfortunately, but this is to be continued. Okay, so growth. Two ways of growing nanoparticle, kinetic growth and thermodynamic growth. I don't think I will have much time to detail this. That comes from a long time ago. We started to decompose RuCot in the presence of an alcohol, and we saw large polycrystalline ruthenium. And also we saw that in a methanol THF mixture, we could control the size of the particle by the amount of methanol we put in THF, which we did not understand for a long time. But in fact, we have droplets of cyclooctane which form in the solution, and they control the growth of the particle. The only message here is that you don't need much to control the size, kinetically, the size of the particle. And we try to look from precursor how we could grow particles. And for example, we use platinum DBA on olefin complex, and we could see that starting from small particles, we could make spaghettis by using an olefin which would direct the coalescence of the particle. With a precursor which decomposes with more difficulty, then in the presence of amine or diamine, we could grow some bigger stuff. But the real surprise came when we took this precursor, which is not really organometallic, which is platinic acid, and then in the presence of oleoylamine, depending on the concentration, we could get either single crystals of dendritic nanoparticles or five-fold and three-fold stars. And we could follow the growth. Very nice. Here we could see that we have some decahedra and icosahedra seeds. Very nice. This is tomography, which shows why we can have a five-fold symmetry because it's not flat in the center. And it's where organometallic chemistry returns. Why is that? It depends on the concentration. In fact, what we could see is that if we work with a low concentration of platinum, the hydrogen uptake is very small. This is the hydrogen uptake in red. So it's very small, and in fact, it corresponds to slow decomposition. But if at high concentration, we have a lot of hydrogen uptake in the solution. Why? Because the 111 phase of platinum is not able to hydrogenate an internal olefin, and the 100 phase of platinum does hydrogenate an internal olefin. So if you have a high concentration, you make a hot spot, you start to hydrogenate the olefin that brings heat, and then there is a burst of, you bring heat from the solution by the chemical reaction. And then you get a dendritic, a very fast dendritic growth. If you decompose slowly by slowly, you make whatever wants to be made, and you expose 111 phases. And so you can find, especially with oleoylamine, which is, in my opinion, the worst ligands in the world, because it's not pure, it has an olefin, it's water. But even with oleoylamine, you can have some surprises. I look at the chairman, but 7 minutes. Then thermodynamic growth. Somebody asked, can you predict what will happen when you decompose? Yes, you can predict, especially after the reaction. And it's what happened with cobalt, because with cobalt, which is HCP, and as if you grow single crystal of cobalt, you have a preferred axis of growth, and you will make cobalt nanorods, and they are monodispersed in diameter and in size. If you go to iron, which is BCC, you expect cubes. And we can make cubes which self-organize into a supercube. This is nice, but can we understand and can we control the growth process? And it took us a while, between 2004 and 2009, to figure out clearly what was going on. And in fact, what we find is that we put an acid, palmitic acid, C16, and an amine, hexadecylamine, C16 also. And depending on X and Y, the more we put palmitic acid, the less we will form an iron 2 complex with 2 carboxylate, and we will decrease the number of nuclei. So the more we put acid, the larger particle we will get. And the more we put amine, the easier we will decompose the particle. Playing on X and Y, we could make a series of dispersed spheres and cubes. They have good magnetic properties. Some have funny properties, like this vortex state, which is between monodomain and polydomain. And the 2 vortex states, you can quench it by a ferromagnetic coupling, or if you put holes in the cube, you can stabilize the vortex. Interest of vortex is they can turn right or left, And in principle, you have 4 ways of storing information over a vortex, but that's another story. And to finish, yes, the iron nanoparticles are interesting, but some of them, again, they burn in air. And when you give that to the physicists to measure transport properties, some physicists don't like. I don't know why, but... And so the idea is, can we make something which is like iron, but which doesn't burn in air? And there is iron carbide. So we took monodispersed nanoparticle of iron, and to put carbide, we were inspired by the Fischer-Tropsch process. You know, the Fischer-Tropsch is carbon monoxide plus hydrogen, which gives gasoline. It was used by the Germans during the Second World War. And when you do the Fischer-Tropsch process, carbon gets inside the iron. So we did that, little Fischer-Tropsch, homemade, and we grew the particle, and we got monodispersed iron carbide particle. If we don't use hydrogen, we can reduce also CO by itself, and we put carbon, but it's less efficient, so we make core shell nanoparticle. And these are the core shell, full carbide, and also we can grow graphene sheet around. Okay, the two which have carbide are air stable. This is loss of magnetization as a function of time. Iron 0 loses 60% of its magnetization rapidly, and the two other only 20%. And then we thought we will combine physics and chemistry. I look at the chairman. He's not moving. 2 minutes. Okay. We will combine physics and chemistry, and we will use the magnetic properties of iron to make catalysis. How do we do that? We take iron, we change in carbide or core shell iron carbide. We put some catalyst at the surface, ruthenium, cobalt, manganese. How do we do that? The same way, iron 0, ruthenium carbonyl, hydrogen, and we deposit, and this is, for example, on a cube. We can see that those cubes by EDX have 5% about of ruthenium on the surface. And then you can admire the, I think it's very clear physics demonstrations here. And when you turn the magnetic moment, you will pass a barrier because you have two stable, these particles are ferromagnetic, and you have two stable positions, and you have a thermal barrier. When you force with a magnetic field, when you force to go over the barrier, you describe the cycle, and the area of this cycle is the measurement of the heat produced by the, this is hyperthermia. And I have no time to show you that, but yes, maybe. This is iron nanoparticle in mesitylene. We put the magnetic field, instantly it starts boiling, which means that the heat is transmitting within 1 millisecond, and we can heat from inside. And we can adjust the heating power. And now we will do Fischer-Tropsch magnetically assisted. And we can do with iron, not very efficient, iron cobalt or iron ruthenium with marvelous machine, homemade. And what we see is that if we heat with hyperthermia, just in a vessel a mixture of CO and H2, then we produce hydrocarbons. We don't see all hydrocarbons, but we produce hydrocarbons. So this is a magnetically induced Fischer-Tropsch synthesis. And we patented that, and actually it's not reported, so maybe I should have, but nevertheless. Okay, these are the complex nano-objects, and as you can see, I will not speak of them. This one has been made, you can recognize this rod. It's coming from Israel, from Uri Banin, and we just put some cobalt on the tip. And this is gold on the tip of cobalt nanorods, etc., and supercrystal. And here it's a growth, self-organization of cobalt nanorods, which grow on an oriented surface. So, to finish, it's not very fashionable to say that you are doing organometallic chemistry these days. People say that it's more fashionable to work in water and to be green, and organometallic chemistry is seen as dirty. But it has some advantages. We can work on the surface chemistry. And there is a lot of surface chemistry still to be known, and there is still a lot to do to control complex reaction at the surface, and also to deposit what you want at the right place to make the device you want. And bon. The ligands are really ligands, not only surfactants. They bind strongly to the surface. You can make bimetallic particles. You can make compounds. I would say that so far, except for cadmium phosphide, we have not proven that organometallic chemistry is very important for quantum dots, but using the techniques of organometallic chemistry, we can understand what's going on during chemical process with quantum dots. Main group, iron carbide, etc., etc. I would like to thank for the quantum dots Céline Néral, Fabien Delpech, Héloïse, Will, Fabien, and Céline are here, and Arnaud Crogagneux. Iron Ancamefre, Lise, Marie Lacroix, and Julien Carré, the physicist who did a lot on hyperthermia, et les autres also. Ruthenium, Karine Philippot, and many people, Patricia Lara, Fernando Novio. Cobalt, Caterina, and few people, and zinc oxide, Myrtil Kahn, Miguel Mandré, and Gregory Spataro. Collaboration, very good collaboration with the physicists, Marc Respo, Julien Carré, people of the magnetic team of LPCNO, Pierre Lecomte for wide-angle X-ray scattering, Etienne Snook for high-resolution electron microscopy, and also magnetic holography, and all the other, Hans Limbar for NMR and deuterium NMR. And this is ERC and all those people. And I thank you very much for your attention.
Thank you. So.